I guess we can get going. So first off, welcome to the club. We are working on, I got to talk to the people at the Hampton Inn to see, because they were discussing the fact that they're going to be doing some major remodeling, and the room that they were going to let us use is going to temporarily be used for staging and storage of building materials while they redo other stuff. So hopefully by the time everybody's ready to get back in a meeting, we will have a space. It was very nice of them, and thanks to Matt for making that contact. It was nice in the EMA, but that ship has sailed. So, and we clearly can't afford to just buy a clubhouse. So, Joe and I were also discussing the fact that we want to do field day again. We all had a really good time, but we've discussed a positive alternative location. We're thinking about doing it possibly at Joe's out there in the country. And I kind of like that idea. So, we would have our own thing. We have, we can set up whatever we need without worrying about interfering with the other club. So I'll put out an email and everybody can kind of weigh in on it. But I really think that's a good idea. And it's closer to home too. So it doesn't have the big concrete box, but I believe that will work nicely. And by then I should have my setup too. So I will have a radio to bring. So, all right, then let's begin with, let me see, I got to do the share thing here. Come on. We're going to do the Pledge of Allegiance. So like we do for everything else, everybody else mute and just kind of say along with me, because the time delay is a killer. So I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation under God, indivisible, with liberty and justice for all. And then a moment of silence for our silent keys. We've actually had 3 from our club in the past year and a half or so. So, all right. And we'll stop that and close that. Now, I think that's all the business we have for right now. We haven't really had a business meeting in a while, but we also really haven't got together and meet. We should, I'm finally going to get back to, it's just too many things going on. We're trying to set up an online payment thing that doesn't cost us a lot, so people can pay their dues. In the meantime, we still need we got to up our insurance with the league for the repeaters and stuff. So we do need to have people pay dues, and it's on the website as to how much it is. So if we can get that done, that'd be great. All right, so now let's introduce our special guest for this evening. Mark is a member of the Ham Radio Workbench podcast. A number of months ago, we had George come on and talk to us. Mark is also the owner of Halibut Electronics. And
my proper title is Head Cheese
of Halibut Electronics. And he's recently decided to make that his full-time job. And he is designing several products, and one of which was entitled SOAR, and he'll explain that. But this will be an interesting look into how something goes from an idea to a sketch to a product that's almost ready to ship. Almost.
Don't get ahead of yourself.
Okay, somewhat close to almost ready to ship, but it's an actual physical thing that he can hold right now. So we will go into that. And ladies and gentlemen, I will turn it now over to Mark Smith, N6MTS, or Smitty Halibut.
Can I have you please enable screen sharing for me?
Yes, and everybody else, please mute. Where are we here? Where are we here? Make co-host. You may now share screen.
Woot, woot. Let's see here. I think I want that one. Actually, I'm just going to go for the app instead. Okay. Can you all see my screen?
Yes.
Okay. Can you see my cursor moving around? Yes, I see a
Yeah.
thumb up. Okay. All right, cool. So my video will probably not actually be down in the lower corner because these are the same slides I use when I'm recording the video to be presented, and I use OBS for that, and I stick my video over that little box. So that's just a box I put on the slides so that I know where not to put content to make sure it doesn't get covered over. So thank you very much, Paul, for introducing me. Again, my name is Mark Smith, N6MTS. I'm also known as Smitty Halibut online in various different places. Mostly Twitter is my most active spot. I am the head cheese, or maybe the big honcho, depending on which title you prefer, for Halibut Electronics, Inc. Halibut Elec is on Twitter, at Halibut Elec, and then the links there are how to get a hold of Halibut Electronics. The webpage right now is laughably bad. I'm actively working on that. I've got a web admin contracted, and we're working on making a better web page. But right now, it will be at electronics.halibut.com. What's there is just a static HTML placeholder. And then I've got a groups.io group. You can search for Halibut-Electronics on groups.io, and that will take you to that page for subscription. There's also a subscription box on electronics.halibut.com. All right, what are we talking about today? Oh, hey, look, what's that? Okay, we'll find out. So why is it that operating FM satellites is a challenge? Why are FM sats a challenge? Well, one of the first things that you want to do when you're operating an FM satellite is you want to have a full duplex radio. You want to be able to listen to the satellite at the same time that you're transmitting to the satellite for a couple of different reasons. One of them is that you want to make sure that you captured the FM receiver on the satellite so that you know for sure that it's your signal that the other person is hearing. And this is more important than on a normal repeater. I mean, it's also a problem on repeaters, but it's more important on a satellite because it's got such a larger footprint. There are oftentimes more people trying to hit it at the same time, and it's a kind of a contesting style, rapid fire, contact happens and then everyone tries to pile onto the repeater, and you need to know when you win, or more importantly, when you don't win. And so to do that, you do full duplex, and you can listen to your own audio on the way down. The other advantage to using full duplex, having a full duplex radio, is that you can listen to your signal strength as heard by the repeater. And one of the ways that you point your antenna is by listening to the signal quality. As the signal quality goes down, your signal strength has gone down, and you can kind of, move the antenna or rotate it to maximize your signal strength into the satellite, as well as the received signal strength from the satellite. Full duplex allows you to do that. The problem is that there aren't any small lightweight radios sold anymore that do full duplex FM. When we say full duplex, I mean crossband, transmitting on 2 meters and receiving on 440 or vice versa. There used to be a bunch of HTs that were sold that did full duplex, but none of them are sold anymore. So like Yaesu had the FT530. I think the most recent one was the Kenwood D72 was full duplex, but not the 74. There is I think it's a Xiegu. It's Wushang. I think it's one of the Wushangs, but there is a radio. I'm getting a thing. Participants can now see my screen. Was my screen not being shared before? No, we're good. Okay. There is a Chinese radio that does full duplex, but it has really bad desensitization problems. So if you are, I can't remember which band is which, but it's like one of the directions the receive sensitivity drops dramatically as you're transmitting. And so that's not good. So the bigger radios, like mobile rigs, can absolutely do full duplex, as well as the desktop rigs like the ICOM 9700 that can definitely do full duplex as well. But those are big and heavy, and sometimes a lot more expensive as well. So nope, just kidding. What is the other thing that makes satellites a challenge? There's a lot of math that happens when you've got a satellite in an orbit flying through the sky and you want to be able to try and talk to that. For example, we want to know when the satellite's going to be in the sky. So there's a thing called TLE, two-line element data. It describes the orbit of a satellite. And if you know the TLE data, then, and you know what time it is, then you know where the satellite is. And you could be able to calculate when the satellite's going to come up over the horizon, or its AOS time, acquisition of signal, when it comes up over the horizon, or its LOS time, loss of signal, when it goes down over the horizon, underneath the horizon behind you. So we need to know that to be able to tell when we're going to be outside. As the satellite is moving through the sky, it also is moving really fast. You know, what is it, 24,000 kilometers an hour or 17,000 miles an hour, roughly, for low Earth orbit. I may have those numbers not perfectly correct, but it is moving really fast enough that you have to compensate for Doppler. As it's coming up over the horizon towards you, it's moving towards you fast enough that those waves are getting compressed, and it shows up to you as a higher frequency. Similarly, when it's going away from you, down toward the horizon, they're getting stretched out, and it shows up as a lower frequency. And so you need to compensate for that. Normally, with a normal radio, you are turning the tuning knob as the satellite is going through the sky. And when it's in the sky, you need to know where to point your antenna.
What?
So you need.
Sure.
Okay. Somebody please, whoever's getting a drink brought to them, please mute.
I got it.
Thank you. So you need to know the azimuth and elevation. The azimuth is kind of the compass heading, and the elevation is how high up over the horizon. And so that tells you where to point your antenna. And that math is all doable. It's all known, but it is a thing that needs to be done while the satellite is in the sky. And you know, if I've got a big radio that's doing full duplex, but none of those radios do that math for you. So now I've got another thing that's doing the math, either a phone or a computer or a tablet or something. And I've got two different screens I need to look at. And maybe I'm lucky that the one that's doing the satellite math is telling me how to adjust the frequency. But now I need to go manually adjust that frequency, or I rig it all together, and now I've made a custom cable, and I've got these two different devices with a janky cable between them. And, you know, because that sort of thing doesn't really exist right now. Similarly, since we're talking about cables, there's audio. For me personally, I like using a headset. I like having headphones on my ears so I don't have a lot of background noise. I can hear what's going on the satellite a lot better. Similarly, I've got a microphone down that's directly in front of my mouth so I can move around, and it doesn't move the microphone relative to my mouth. And I don't have to have something in my hand up to my mouth, because I'm also holding the antenna with the other hand, and I'm trying to write down my logs with my third hand, and I'm trying to tune the radio because of Doppler shift with my fourth hand. Right. You know, so it's just, I'm running out of hands. So, you know, one of the complexities is routing all of that audio from all the right places into the headset for me. Right. And so now I've got either an HT, you know, I found an unobtainium used radio. If you're lucky. If you're not lucky, maybe you're using two HTs, one for uplink and one for downlink, but now I've got to route the audio into that. Or the headset to, like, you know, the bigger expensive radio. The other thing that we really like to do when operating satellites is we like to record the audio of the pass. The primary reason for this is that it is so quick fire. The QSOs are so quick that you will operate the other station very quickly, much more quickly than you can typically write it down while you're also tuning the knob and doing all of the things. So one advantage is to be able to record the pass. You make the QSO and you're like, all right, that's recorded. I don't have to worry about writing it down and remembering what their grid square was or anything like that. Then after the pass is done, you can go back and listen to the pass and do all your logging after the fact. That is a very common thing to do. But if you're going to hook that up, now you've got a third device because you've got a recorder and your radio, possibly two radios, and the thing that's doing all of the math calculations for you and controlling everything. You just have this giant mess of cables and devices. What would an ideal appliance for FM satellites look like? Well, the easy answer is it's something that does all of those things, all built into a single device. Enter SOAR, Satellite Optimized Amateur Radio. Whoops, hey, don't go too far ahead. I happen to have a SOAR right here. And of course, the power is on the wrong side, so the cord is getting dragged. But this is what the device looks like. And this is the revision B hardware that's much closer to what's actually going to go to manufacturing. I just received these a couple of days ago, so I'm working on some final testing and some other things. But this is what it looked like when I put this slide deck together. Satellite optimized amateur radio. The first thing that SOAR does is that it has separate VHF and UHF radio modules. So these are the SA868. If you've ever heard of the DRA818 or the SA818, it is a very similar module to the DRA818s. The distinction is that the SA means that it's made by N6RF instead of Drogi. It's a different manufacturer, but otherwise the module is identical. And the 868 is the 2-watt version of it. The 818 is only a single watt. So it's slightly more power, and it's made by a different company. I believe the SAs are actually the originals, and the Drogi makes the clones. I'm not 100% sure on that, but I think that's how it is, because N6RF has continued to advance the development of these and is making newer models and other modules like this. Whereas Drogi, I don't think is. I think Drogi is always a little bit behind. So I think Drogi is the one who makes the clones. But we've got two modules in here, a VHF module and a UHF module. And the modules don't share any components. So they operate completely independently from each other, which allows me to transmit on one and receive on the other at the same time. We do need to filter the signals to be able to do that. So here you can see the bandpass filters, very messily assembled one, I might add, but the bandpass filters on each of these modules. The top one is the VHF module, the bottom one's the UHF module. And the bandpass filter is what allows it to operate full duplex. So on the VHF radio, I've got a high pass part of the bandpass, which is filtering out all the lower frequencies below VHF. That doesn't really help us in this particular case, but it blocks out things like a strong by FM broadcast station or like an HF station if you're near an AM broadcast tower. Just anything below the 2-meter band. That's less of a concern in the immediate radio, but it was easy enough to build, so we put it in there. More importantly, the low pass filter, which blocks the higher frequencies than VHF, does two things. One, it blocks off it filters out any harmful harmonics that these modules might be putting out. These modules are basically Baofeng radios. They are the same chip, the R something 1862. I'm going from memory on it. I want to say RSA, but I know it's not RSA because I would remember that. Anyway, it's the same chip, FM chip, that's used in a lot of the Chinese radios. So we need to filter off the high-end harmonics. That is definitely a requirement for it to be legal in the United States. But the other thing that the low-pass filter does on the VHF side is that whenever the UHF radio is transmitting, it knocks down that transmit energy enough so that it's not going to desensitize the VHF radio. And that's what allows the full duplex operation. Similarly, on the UHF side, the high pass, which is blocking low frequencies, part of the bandpass filter on the UHF, so that high pass is going to block out the VHF transmitter. So whenever the VHF radio is transmitting, that high power is going to get attenuated before it hits the front end of the UHF receiver. And that's what allows the UHF receiver to receive while the VHF radio is transmitting, right? And then we also have the low pass, high block part of that bandpass, which is doing the harmonics, right? So we've got bandpass filters on both of these modules, which is what allows it to operate in full duplex with little or no desense. SOAR also does all the satellite math. It has a Teensy 4.1 which is a redonkulously powerful microcontroller on it. So it has plenty of horsepower to do all the math, but more importantly, it has a GPS. And the GPS on SOAR, right now I've got this little tiny antenna that I built hooked up to it, but it will work with any sort of a GPS antenna, even active antennas, which I have one right here. So let me go ahead and hook it up. Not that it's going to matter to you anyway, but it has a GPS antenna, so it knows where and when it is. And the where you are is important, and the when it is important for being able to figure out where you are relative to the satellite, because you need to know where you are and when it is to be able to figure out where the satellite is in the sky and how fast it's moving relative to you, to do all of that satellite math. So the GPS is already built into the radio. It can automatically figure that out. You can download TLE data, current TLE data. It changes periodically. For most passive satellites, it doesn't change super often, but for something like the International Space Station, which routinely gets relifted into orbit, its orbit gets lifted up higher, it changes periodically. And so you need to be able to download new TLE data onto the radio. This is done. The radio internally has an SD card on it. Thankfully, you do not have to open the radio up to put new data on the SD card. When you connect it to a computer over a USB cable, it will show up as a MTP device. It's not quite a bulk storage device. It doesn't show up as a USB stick. Excuse me. It shows up as, it looks like a mobile phone. Like when you plug a mobile phone or a camera into the computer, and then you can copy files to and from that. That's what it looks like. So you can copy current TLE data directly to SOAR from your computer, and you will have to do that periodically. So it knows where the satellites are, and from that it can automatically calculate all of the acquisition and loss of signal times. It can do all of the satellite predictions, the same things that you would get on your phone with, like, GoSatWatch is the one I use on iOS. I don't know what the other apps are that are out there, but all of the satellite prediction apps that tell you when something's going to be in the sky and where to point your antenna and all that. It can do all of that for you. It can also calculate relative velocity. It's very similar math. And once it knows that relative velocity, it can calculate the proper Doppler shift and automatically apply it. So it knows which satellite you're talking to and where it is and when it is and how fast the satellite is moving relative to you, and is able to automatically adjust your operating frequencies for that Doppler. So you no longer have to twiddle the knob to adjust that for manually. It also is able to calculate azimuth and elevation and put that on the display. So it has the little SkyTrack, the circle over here with the azimuth and elevation. Azimuth is where on the circle it is, and elevation is, 0 elevation at the horizon is on the outside, and then directly overhead is right in the center. It's a standard SkyTrack, and it can display that on the screen while the satellite is in the sky. Okay, audio. What else does it do? It is optimized for headset use. The whole idea, the way I designed it, is that you just plug a headset directly into the side of the radio, and all of the audio is routed to the correct place. There are many different headset standards. If I chose like Heil Pro 7, then there would be a bunch of other headsets that it doesn't work to. There's so many standards. You just got to choose one and accept that you're going to have to adapt to get to all the other ones. So I chose one that was, quite frankly, easy for me to manufacture, and also has available very inexpensive, easy to get a hold of headsets. And that is the PC gaming headset standard. It's a 4-pin TRRS 3.5 millimeter socket. Left and right audio on the tip and the first ring, ground is the second ring, and then the microphone audio is on the shield. Sometimes that ground and shield are reversed depending on whether your headset is for a PC or like an iPhone, or if it's for, I think, PlayStation uses the other standard, and I think old Android phones might have used the other standard. I don't remember exactly which, but you can switch between the two using jumpers inside the radio. There's a little jumper block that you can rotate the jumpers to choose the other standard. So it will work with both. It also, on the exact same storage, can record the audio of the pass directly to internal storage. All of the audio from the radios and from the microphone get routed to the microcontroller. And so the microcontroller internally can record that audio directly to an SD card. And when you plug it into your computer, it will show up. Oh, sorry, getting ahead of myself. It can be played back directly on SOAR. And we'll talk a little bit more about that in a bit. So you can, as soon as you're done with the pass, you can go back and say, play back that pass and listen to it again. It records your microphone audio, so the uplink audio, and the radio's receiver audio, so the downlink audio, in separate channels. It's just using a standard stereo wave file, so one's in left and one's in right. When it does playback, it'll probably give you the option of mixing them together, so it's not quite so separated. But it does record them totally separately so that you can listen to one very carefully without having the other one interrupt or whatever. But yeah, so you can listen to it directly on SOAR. It's also available as a web file over the USB. So when you plug it in to download the new TLE data, similarly, there will be a bunch of WAV files there of those recordings that you can copy off. All right, so the other thing that other radios don't do is I designed SOAR with a bunch of outputs that are going to help me design future products. The first one is pretty easy, but there's an external PTT, just a simple contact closure, tip and shield, another 3.5 millimeter socket, tip and shield, contact closure to trigger a PTT. There's a PTT button on the radio itself, so if you don't want an external one, you can just use that for testing or whatever. But this also allows you to run a PTT up to the boom of the antenna. You're holding the antenna in your hand, just stick a little PTT button there. Or maybe a foot switch or an elbow switch, whatever it is that you like for triggering PTT, it is broken out onto its own connector. So like on HTs, the way you trigger a PTT is by grounding the microphone and allowing DC to pass through the microphone. Well, if you were to run that over to a foot switch, that means you have your microphone audio going all the way down to the foot switch and back up again, or all the way out to the antenna boom and back up again. You don't want to do that. So this breaks it out into its separate connection with a little bit of RF choking on the inside. So if any RF gets picked up on that wire, it gets choked out before it goes into the radio. So that makes it a lot easier to use that external PTT. You can mount a button on the antenna boom or a foot switch, or my friend Dan is actually designing a handheld switch that you can slide the boom into. And we've got some other ideas for that one as well. I am also making azimuth and elevation data available over a serial port on, you guessed it, yet another 3.5 millimeter TRRS cable. It's going to have ground, power, transmit, and receive data. But it's going to spit out the azimuth and elevation numbers like every second or a few seconds or whatever over that serial port. That will allow us to build a tiny microcontroller that gets mounted on the boom of the antenna. Let's put a magnetometer on that microcontroller so it knows where north is, and an accelerometer so it knows where down is. And if you know where north and down are, and you know the azimuth and elevation of the satellite, you can calculate a diff of that and display it on a screen. And that will help you say, all right, you need to point your antenna, higher or more to the right or whatever. And that will help you point your antenna in the right direction. So we can build like a little targeting display and mount it to the boom of your antenna. SOAR is designed to output the data that's needed for that as a future product. Or you could build one yourself if you wanted to. All right, so what does the user interface of SOAR look like? I actually don't think I have a slide for the physical interface, but let me go ahead and show it to you. It is a roughly 4 by 5 inch box. That's a little over an inch thick. For the metric folks, it's 100 millimeters by 120 millimeters by, I think, 35 millimeters tall. It's got a 2.8 inch TFT display, a volume knob and an encoder wheel and a back button. Between the encoder wheel and the back button, you can navigate just about any menu you need. But I also gave it these 5, I call them PF buttons, or programmable function buttons. They correlate to little icons at the bottom of the screen. So the icon at the bottom of the screen says what that button does at any given time, and it allows a very flexible user interface to be established. It's very similar to how the Kenwood does theirs. The D700 is, in my opinion, one of the best mobile rigs ever made, period, full stop. On the 710, I just don't have any 710s, and it uses that same method. But using those as physical controls, there are 4 primary operating modes of the radio. We call them views. The first one is as a standard HT, because sometimes you just got to talk to your buddies on the repeater, right? And so the standard HT has both a VFO mode and a memory channel mode. And you can just, you can set CTCSS tones, your squelch, high and low power, all the things that you would expect out of a standard analog FM HT, you can do on SOAR. We also have a pass prediction page. And so that's where it's doing all of the future math, right? I know about the satellite. I've got current TLE data. I can either use my current GPS location and predict the time that it's going to be there, or you'll be able to tell it, pick this latitude and longitude and this time, and then give me predictions. So like if you're going to be going on a trip, 300 miles northeast of here and in 2 weeks, right? You can plug all of that in and it will calculate all the passes at that time. I haven't designed that screen yet, so I don't have anything to show for it, but it will be there. And then pass operation. This is where you've got a channel that is defined for a given satellite. And that channel specifies the center transmit and receive frequencies, or uplink and downlink frequencies. And it's associated with the name of the satellite in the TLE data files. So the TLE data files are downloaded from a website called Celestrak. They're calculated by NORAD. Yes, that NORAD. They're the ones that are tracking all of the satellites up in the sky, and they publish the orbital parameters for everything that they're tracking, including all of the ham satellites. So you just download that, stick it on here. With that TLE data and knowing the center frequencies, it's able to calculate the current Doppler shift. So right now, this is saying it's -4 kilohertz and +1 kilohertz on the VHF side. And it automatically applies those. So if the center frequency here is 437.8 and the current Doppler shift is -4 kilohertz, the actual receive frequency would be 437.796, right? So it does all of that automatically for you, and these numbers get updated as it's moving through the sky. Now, this is a little bit of a weird example because the elevation is negative, meaning that the satellite is below the horizon. So this screen capture was taken when this particular bird was not in my sky. You can also tell that because the red dot on the SkyTrack the dot on the SkyTrack is red. That is the dot that says where the bird is. But it tells you, roughly where in the horizon it would be. Anyway, so that's the pass operation screen, and it's channelized in all of the features that you might want are there and quick to get a hold of. One other neat feature is that because it knows when AOS and LOS are, it can automate a few things. For example, at AOS, when the bird comes up over the horizon, it will turn your squelch down to 0. It opens up your squelch automatically. So, you could use that as an indication of, oh, hey, look, a bird's in the sky. Instead of, you're sitting there eating a donut or whatever, and you lose track of time. Well, it's going to open the squelch and tell you that it's there. Similarly, it will automatically start recording for you. And you can also configure it to say, give me 1 minute before AOS and 1 minute after LOS if you wanted to, or something like that. Anyway, and then the fourth mode is pass playback. Pass playback looks very similar to the pass operation page because not only does it record the audio, it will also record the state of the radio at the beginning at AOS, right? Or at the beginning of the recording. So it will record your latitude and longitude. It will record the time and all of the things that needs to be able to recreate what's on the screen at the time of the playback. So it coordinates the audio playback with the display of information on the screen. So you can see on the screen exactly what was on the screen at the time that that recording was made. Hardware. All right, let's talk a little bit about the history of this. Where did I get this idea? Well, this started as a very quick, hang on, let me put my phone on Do Not Disturb because I foresee a thread starting. Okay, it started as a very quick Bring a Hack Day project to Maker Faire 2017. I was invited to an after party at Maker Faire 2017, and it was a Bring a Hack thing. And I'm like, okay, I've been thinking about the satellite problem for a while. Let me see what I can bang together with parts on hand. And I literally designed this board in, I think, a day and a half. I had it sent off to Osh Park for fabrication, got it back. It took me like an hour or two to assemble it. There were so many problems with this board. Oh my gosh, I don't even want to start thinking about it. You'll notice that this chip isn't even populated. This socket isn't on the board. Like this capacitor wasn't there originally. There's a bodge wire right here. All of this audio stuff was just completely broken. This header here, I don't know if you can see the wires connecting it, but I got the power and ground reversed. It was a disaster. But after all of this bodging, it was enough to prove the concept. I was able to transmit and receive simultaneously, and I was able to control the frequencies from the microcontroller. I never made it as far as doing any of the recording, or actually this one wouldn't record, or do any of the automation, but I proved the concept that the full duplex operation was a thing, and that controlling the radios in real time from a microcontroller was a thing. And I got super excited, and I took all kinds of notes about what I wanted to do in a version 2, and then promptly set it down and forgot about it for years, like so many projects. Version 2. So 2021 was a rough year for me. I'm not going to go into the details, but suffice to say that my employment status changed around September, October-ish of 2021. And I knew that I was going to take some time off from working. I wasn't going to go look for another job immediately because I needed some time to unburn out. There's a more succinct term that I use, but I won't use it here. I needed to recover mentally. And so I knew that I was planning on taking several months of time off between jobs. And I promised myself, I'm not just going to sit around the house. I'm going to start working on some of these projects that have been sitting on a shelf for years. And one of them was SOAR. And so I started looking at what I had done at Maker Faire, 4 years prior, and thinking about what it was that I wanted to do. And I started talking to Patrick, WE9, I can't remember his call sign. Patrick Stoddard. He's down in Arizona. He's a huge in the satellite community, and chatting with him about what this device or this kind of device should have. And so I started hacking together a prototype. And here is a Teensy. I know I wanted to upgrade to the Teensy from the Arduino Micro is what I used the first time. I wanted a bigger screen. I wanted a GPS. Here are the 2 radio modules. These are some prototypes. There's a little dummy load. And I just started hacking together things with a bunch of fly wires like you can see here, right? And laying out some very loose and spread out prototype PC boards. And this was what the prototype ended up looking like. And so it's a roughly 100 by 100 millimeters because that's what's easy to get manufactured. It's a stack of 3 boards. The top board just had all the user interface stuff like the display and the buttons and the knobs and things. The bottom board was the RF board. It had those RF modules, the SA818s or 868s, the RF connectors, and I also put the power there. So the switching power supply input there. And then the middle board was all of the digital and analog. So the microcontroller is on here. It's right behind this connector. All of the audio processing. So the audio comes up from the RF board through a header over here into the middle board. The headset plugs in here and stuff like that. Right. So the idea, though, was that I separated all the functions into different boards, which allowed me to iterate on each individual part of the project individually. Like I ended up building, I think 2 or 3 different revisions of the RF board, 3 different revisions of the digital and analog board. And I think I only needed 1 revision of the UI board. The UI board was pretty much right from the get-go. But I had to iterate on these things to kind of nail some things down. And this was my prototype hardware. I never intended to sell this. This was always laid out with the intention of it being, big and spread out. But while I was doing this, I was really kind of realizing that this could be a day job for me, right? Rather than looking for another job in IT, where I've been doing system administration and network engineering and information security for 30 years now. Like I just wasn't feeling drawn to that, but I was feeling drawn to this. And so I'm like, okay, this is, and I started running the numbers, and I'm realizing like this could be not just a one-time project for myself, but an actual product that I sell. And so I started the business, Halibut Electronics, and I started working on version 2.2. This is what I'm calling, I did a 2.0 and then a 2.1. And then this is what's 2.2. And 2.2 is the production hardware, not the prototype hardware, right? This is the one that's actually laid out in a way that I would expect to sell it. This is the revision A, very minor versions from the outside. This is revision B, but the inside, there are a lot of changes. But this is what the product is going to look like. And it's, 4 inches by 5 inches by about 1.25 inches small. So not huge. It's very lightweight. It does not have internal batteries. So you will need to provide your own 12-volt source. Really, anything between 7 and about 40 volts will do fine. It's got a switching power supply in there, so it'll switch that down to the internally. It uses 5 volts. And it needs an external GPS antenna. I will probably be, unless I can find a better answer, I'll probably be giving out these little things to go with the radio. But I might be able to find a better antenna somewhere else that's not ridiculously expensive. Yeah, but that's what the 2.2 hardware looks like. This is the inside of the board. So I took those 3 separate boards and squished them down into one board, right? Here's the RF and the microcontroller all on the same side. On the other side, we've got the display and the buttons and the knobs. And then here's some audio processing. There's a little bit more under the display, right? So I squished all of the functionality of those 3 different boards into one board. And that is what's going to go to production. There have been some more changes since these pictures were taken. So it won't look exactly like this, but it gives you the idea. Oh, there's Rev B in fabrication as of earlier this month. Like I said, I just received them. So that's what this is. But that gives you an idea of the complexity of the project, right? So this is a 4-layer board. Anything that's red is the top layer. Anything that's green is the bottom layer. And then purple and yellow are the 2 center layers. And most of the signals are routed on the inner layers and then sandwiched between giant copper pores, giant sheets of copper on the top and bottom layers, which acts as insulation or shielding. That's the word I was looking for. And so it shields most of the signals on the inside of the board away from all of the RF that's in the outside environment. Possible future ideas. I am not committing to any of this. You cannot hold me to it. But this is what I'm thinking about that I want to do next with SOAR. So we already talked about the azimuth and elevation outputs. I plan on making that formatted such that you can plug it into not just a little targeting computer, but also to an azimuth and elevation rotator. Right. So there are ASL rotators out there that already have control protocols in them. I will build to those protocols. So you should be able to, with a simple adapter hardware, connect SOAR to one of those ASL rotators. I've already got USB audio working. Since the audio goes into the microcontroller, both uplink and downlink. I also made audio output from the microcontroller go into the headset and into the mic audio on the radios, which allows the microcontroller to completely send audio to and get audio from those radios. And I've also already got it working so that that'll show up as an audio interface on the computer. I get that pretty much for free with the Teensy. That was already implemented for me. Excuse me. So all I have to do is implement a CAT control protocol over the serial port so that when you plug it in, it shows up as a serial port and as an audio interface, just like an ICOM 9700 or 7300 or whatever. That would allow you to use this as a remote station or some other internet controlled or computer controlled FM radio. It's not nearly as capable as the 9700 because it is limited to FM. Those radio modules are audio in one side, FM modulated RF out the other side. I cannot do arbitrary waveforms on those modules. So like I can't do single sideband or DMR or anything like that. It has to be something that's modulated on top of FM. But, you know, for a reasonably priced product, being able to do all of that over USB sounds like a pretty neat feature to me. Like I said, there are various AFSK modes, audio frequency shift keying. So for example, packet, right? Standard 1200 baud packet is just audio shift keyed audio signals, frequency shift keyed audio that is sent into the FM modulator, right? That's how normal packet mode works. So we can do that in this radio. And there's plenty of horsepower on that Teensy that I could do the actual packet modulation and demodulation in the microcontroller. And so we can do on radio straight up packet and, you know, present a TNC interface out to the serial port, or we can do APRS built in, just like the D700. Another possibility is SSTV. SSTV, like the thing that we just had with the ISS back in December, that is an audio signal that's sent into an FM modulator. So we are demodulating that FM, we get that audio goes into the microcontroller. That microcontroller could be programmed to decode that slow scan TV and display the image on the radio, or save it to file, save it to a file on disk. And because it knows where the satellite is in the sky, it can do automatic frequency compensation for it. It can do all the same Doppler shifting that your normal radio doesn't do. Right. So all of those are possible. These are not version 1 features. All of them, let me rephrase. All of this is possible with just software changes. So if you buy the radio now, a future firmware update, which I'm never going to charge for, don't worry. Firmware updates will always be free. But a future firmware update will make that possible, or can make that possible. This one I'm less sure on, but it's possible that we might also be able to do other constant amplitude FSK modes. For example, 9600 baud packet. 9600 baud packet is not just a audio tone sent into an FM modulator, and that FM modulation gets sent out over the radio. It is directly modulating the FM, or the RF carrier. It is directly modulating that RF carrier. But it's modulating the frequency of that RF carrier, which is what frequency modulation is. And the limitations, what stops an FM radio from being able to do 9600 baud packet, is that it rolls off the low frequencies below 300 hertz and the high frequencies above 3000 hertz. And so if, without those low frequencies, you can't make, you can't shift it up to a frequency above your center and keep it there, because that'll just gradually gravitate back toward the center frequency. Similarly, without the high frequencies, you can't make sharp corners on your frequency jumps. So there are some limitations there, but that's all audio passband limitations. I am designing the audio parts of SOAR to have incredibly wide bandwidth. I'm designing it for 16 hertz to 16 kilohertz. The FM modules I'm using, when configured for FM audio, pass 300 to 3000, standard communications grade audio. But in software, there is a high pass filter that you turn on to get that, a low pass filter that you turn on to get that, and a pre-emphasis filter, which I'm not going to go into the description, but it's another thing you do when you're sending audio over FM that you don't want to do when you want to do something like 9600 baud packets. And I can turn these all off in software. What I haven't done is measured what the frequency throughput or what the frequency roll-offs are on the high and low end with those filters turned off. If it's enough to be able to directly modulate that FM carrier, then all of my other stuff, all of the other audio paths in what I'm building have a wide enough frequency range that we should be able to grab that FM carrier by the brainstem, grab it by the DC or 1.6 hertz, close enough to the DC, and use it to modulate constant amplitude FSK modes like 9600 baud packet. Or another example is anything that's GMFSK. For example, like the new packet radio stuff. I don't know if you've heard about NPR, the digital, new packet radio is what it stands for. Go look it up. I don't know the details of it, but it's a GMFSK signal. M17 is another GMFSK signal. M17 is it's a protocol that's being developed right now by a worldwide group of hams. I'm kind of tangentially, I got my finger in that pie, but I'm not active in it. It's a replacement, not a replacement for. It is an alternative to the existing digital voice modes that we have now, right? So it's trying to solve the same problem that D-Star and Fusion and DMR are trying to solve. The big difference between M17 and those other ones is that M17 does not use the AMBI codec. The AMBI codec has really limited what we can do with those digital modes legally. If you're willing to kind of play it fast and loose with some patents, you can install a software encoder and decoder on your system and do anything you want with all of those protocols. But that's not technically legal. You have to use the AMBI encode chips that the company that does AMBI, I can't remember what it's called, sells. Like there is no freely available software encoder for non-commercial use. And a lot of us, free as in speech kind of open source people don't like that about DMR or D-Star or System Fusion or P25 or anything like that. And so there was this move to come up with an alternative that uses the free DV, no, that's the modulation. Codec 2 is what it's called. Codec 2 is a voice encoding algorithm that is completely free and open source. Free as in speech and free as in beer. And so M17 was developed around that codec. And then we also took a lot of the things like DMR was not really designed for ham radio. So it doesn't use call signs. It uses this arbitrary number that we have to map between call signs. And if you go to radioid.net and you get your DMR ID, that's what that is, right? M17 does away with that. We encode the call sign directly into the headers, things like that. So anyway, M17 is a GMFSK signal. If I'm right about what those RF-FM modules are capable of, we should be able to put M17 and NPR directly onto SOAR. Boy, that went way too long. All right, possible future hardware ideas. These are even less committed than what I've mentioned on the previous one. These actually require either hardware upgrades or changes or additional hardware. Remember I talked about that boom mounted targeting display? I want to build that. I want to build one of those. I've had a lot of people ask me to build a lightweight azimuth and elevation rotor. I am not a mechanics guy. There are lots of designs out there. I may consider, if I find one that would let me do it legally, I may consider manufacturing an existing design and maybe tweaking that design. But I'm not really a mechanics guy. Another possibility is that I may team up with somebody who is a mechanics guy and we build a lightweight azimuth and elevation rotor. But I will definitely be supporting whatever rotors are already out there made by other people to the best that I can. More power. So those radio modules that we're using only output 2 watts. They claim 2 watts. I think the spec sheet, when you look at it, actually says 1.8 watts. So I think they're rounding up when they call it a 2-watt module. And then my bandpass filters have, I think, about 1.4 dB, 1.5 dB of insertion loss. So by the time you lose from the insertion loss and whatnot, you're down to about 1.25 to 1.3 watts. If you are the only one talking to the satellite, that's enough to make it to the satellite. But if you're trying to compete with anybody else, excuse me, that's not going to be enough. So I acknowledge ahead of time that this is a relatively low power radio. So one of the things that I'm going to want to build is an external amplifier. I am designing the radio right now with the external amplifier keying available. So there's the 4th TRRS 3.5 millimeter socket is labeled amp, and it's 2 opto-isolated closures, one for when it's keying up VHF and one for when it's keying up UHF. And so that will trigger an external amplifier for each of the bands. And also on the preamp. The receiver is pretty good. It could be better. We probably have about 5 dB. It's less than 10 dB. We have about 5 dB that we could improve. So it would probably benefit from a preamp. And if I'm going to go ahead and build an amplifier, I might as well stick a preamp in the bypass path. Those FM modules, it would be really nice if I could replace those with a different module that had RF in one side and arbitrary I and Q out the other. So I and Q, if you don't know what that means, don't worry about it. It's SDR stuff. Basically, I want to replace it with an SDR. Again, this microcontroller is redonkulously powerful. It's like a 600 megahertz 32-bit processor. I mean, it's way more capable than we need. But that capability allows us to do full-on like RF signal manipulation. And so if I could get I and Q out of a radio and into a radio, that would allow us to do things like single sideband or CW or FT8 or FT splat, all the other modes that happen on these satellites, not just FM satellites anymore, but the linear transponders. This SOAR won't, in its current incarnation, will not work on a linear transponder because they don't like FM. They don't like constant amplitude modes on the linear transponders. It's frowned upon. So if I could replace that FM module with a narrowband SDR, I would love to be able to do that. I've got some ideas. Go look up a chip. If you're really curious, go look up a chip called the CMX991. And I'm keeping an eye on that chip and may want to try and build an SDR module out of that. But that's pretty much it. SOAR, Satellite Optimized Amateur Radio. There are the links to learn more. Well, eventually, once I actually put things on those links. But the most important one right now is the groups.io. I send periodic project updates out to the groups.io. Whenever I get new boards or implement a new feature, they're the first ones to find out about it. The groups.io is also where I'm going to go to look for early adopters. So if you are one of those that's saying, shut up and take my money, join the groups.io because they're going to be the first ones to get dibs on these things. My goal is to make a first batch of somewhere between 50 and 100 within the next few months. I got a lot of firmware I still need to write. I was planning to try and make it to Hamvention. I don't think I'm going to make it to Hamvention. In fact, I've already decided I'm not going to make it to Hamvention. So I will not be there and I won't have radios with me at Hamvention. But right around that time or a month or two after that, I'm going to be making radios available to the folks on the groups.io, kind of the first batch, and get a bunch of feedback from them, see what they think, what they like, and then, hopefully incorporate some improvements in the next version and then go public with it.
Very cool.
That's it. Thank you very much.
Oh, thank you,
Any
Mark.
questions?
Yes, I have one. So it will automatically figure out the split or the reverse split depending on the TLE data, right? It'll know if a repeater is VHF, UHF up, down.
So the TLA data does not contain the frequency channels.
Okay.
AMSAT publishes those, whoever, all of that is public data. So that will be programmed into the channels.
Right.
The channels on here, the memory channels, is just a JSON file on that SDR card, on that SD card. So you'll be able to edit it on SOAR, go into VFO, set the thing up the way you like it, and then say, save this to memory. Or you can just plug it into your computer, copy that JSON file off, make any modifications to it that you want. I'll probably make a tool that will help you do that. Or you can just edit it by hand and then copy it back onto the SD card. And all of that will be there. One of the fields in the memory channels is what satellite is associated with this channel. And the TLE data as distributed by Celestrak, each satellite has a name. I don't think those names have changed over time. Maybe they have, I don't know. But whatever that name is, if that name shows up in a memory channel, then SOAR says, aha, this is a satellite channel. And it will use, when you go to that channel in the satellite operation mode, it knows the frequencies from the channel. It knows all the, CSS tones, CTCSS tones, power, blah, 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 all the radio side of things. And then it gets the TLE data from the other file, but it uses that name to associate.
Okay.
Records.
So it can duplex either way.
Mm-hmm.
Cool. All right.
Yep.
We do have a question. What is the target price? I know the answer to this one.
Yep. So here, let me stop sharing. Target price. I am unfortunately not able to give you an answer on that. I have an answer, but I'm not giving it out yet. The reason for this is I know what the bill of materials is, and I know how long it takes me to assemble one. It takes me enough time to assemble one that I know that I am not going to be assembling these. So I am presently in the process of getting quotes from manufacturing houses to see what it's going to cost to assemble it. In fact, I was literally contacting manufacturing houses today about that very issue. Once I know what that's going to cost, then I will be able to put out a price. I will tell you it's going to be more than $100, and it will be less than $1,000. And when I say less than $1,000, I don't mean $999.95. That's not the kind of less than $1,000 I mean. I mean actually less than $1,000. It'll be somewhere in that range, though.
Okay. Anybody else have some questions?
I have one question.
Yeah, go ahead.
Yeah, would there be any appeal for a boom mounted radio with a remote UI?
It's an interesting idea. You're not the first person who suggested mounting the radio itself to the boom. I don't see the benefit to that, but I'd be curious to know why you would want to put the extra weight on the boom itself.
Well, I would put the radio on the boom because the feed lines would be short and the boom would be on a tripod out in the backyard, and I would be in here out of the weather where it's warmer, and I would have a remote UI that could be anything.
Okay.
Could be wired or it could be Bluetooth.
Okay. I see where you're going with this.
And also it would handle the LAS drive.
So you're talking about having an azimuth and elevator, ASL rotator, out in your yard, mounted somewhere, put this radio close to it so it has short feed line. And so really it is, how do you control the radio remotely? Okay. I had not thought about that. Let me get back to you on this. It would not be Bluetooth or Wi-Fi because the radio does not have that capability on it. It does, however, have a serial port. And it's also got USB. I would have to get back to you on that one. It's not currently a design goal, but I'm trying to figure out whether it's something that could be done with just software.
Would it be wired?
That would probably, well, Probably. If it's not wired, then it would definitely have to require extra hardware, because I don't have any way of communicating with SOAR wirelessly right now.
We probably want to be able to go 50 feet. So that might be a problem with some.
Nah.
Okay.
No, 50 feet over a
But I'm in here where it's nice.
No, I respect that. 50 feet's not a problem over Twisted Pair. That's not a problem at all. You can go several hundred feet with the right signal over Twisted Pair. I would probably go to like RS 485, although that's half duplex, so I don't know.
422 and 422 full duplex.
Yeah. Yes. You're right. 422 is the balanced version of 232, right?
Mm-hmm.
Yeah. And then 485 is the multi-drop thing. Okay. And then we'd also have to send transmit and receive audio. Yeah. Anyway, let's talk afterwards. It is not currently a design goal. I like where you're going with it, though. That is honestly probably a different product. This is really designed to be lightweight and portable.
I would agree with that.
Yeah.
Yeah.
But I guess I'm thinking about a totally different type of operation. I think where you're coming from is standing out and looking up at the sky, and I'm talking about being inside.
Yeah.
Yeah. Join
using
the
external equipment.
Join the Groups IO group. That's the good place to discuss things like that. Yep.
Yeah. I like where you're going with that, though. This is one of the reasons why I love talking about this, is because y'all always come up with these wonderful ideas that I never thought of, right? The whole idea of using this over a USB cable as a remote base, connecting it to a computer, that came up in a conversation I had with an ex-coworker of mine when I was telling him about this. He's like, that would be so cool in this use that I have. And I'm like, I never even considered putting a cat cable on it, right? Because I've always considered it as something that's hanging around my neck when I'm out, like on a lanyard. That's why it's got these little hoops on the board, so that you can like connect it to a lanyard and literally hang it around your neck while you're out in the field. And so, you can pick it up and operate with it and then just drop it. And it just bounces off of our, my copious belly. I don't know. I'm not going to speak about yours, but plenty of padding down here. It's not going to hurt anything. And pick up your antenna and start operating the satellite. So I love these other ideas that I get from y'all. So thank you.
We do have a question. What's the viewability of the display in daylight?
Okay. I haven't tested that. I'm going to be perfectly honest with you. I will do that tomorrow. You are not the first person to ask me that question, and I haven't tested it. I have used the radio outside, trying to mostly listen to satellites. This is before I got the transmitter working correctly, but the receiver was working, and I could use it to frequency track the satellite. And I don't remember having a problem with the display, but I wasn't explicitly looking at the display.
Okay.
Or I wasn't explicitly testing the display. I was out there trying to test the frequency tracking and the sky tracking. So I will take it out tomorrow when it's bright outside. Heck, I can probably still do it tonight. Thank you, West Coast. I might be able to still do it tonight and take it out there and take a look at that. I'll get on the groups.io and ask me the question there, and I'll answer it.
Cool. All right. Anybody else have any questions?
Yeah, I got a quick question.
Yeah.
Is there any one of those teensy modules that be compatible pin for pin with that have Wi-Fi on it?
No.
Or is that not a thing?
No, Teensy doesn't have any Wi-Fi on it. I is seriously considering adding an ESP, like an ESP01 or something like that. Honestly, I ran out of serial ports. There is no GPIO left on this thing. In fact, I had to add a shift register so that the 8 buttons on here only take up 3 pins on the microcontroller. So I had to increase the BOM cost to be able to save some pins so that I could do all the things that I need to do.
So the reason I asked that is, and it was funny that you mentioned making a lightweight azimuth elevation rotor. That's something I actually looked into building last year. Never got around to it, but part of my design was I was going to use an ESP 32 that had Wi-Fi in it, and I was going to have the thing join your Wi-Fi network and offer a web page for its interface. So you could use either a smartphone or you could use your computer. And when you had mentioned, you know, the file on the little card inside was in a JSON format, you know, it immediately made me think of the web. And, you know, boy, that would be really cool if it had like a web interface where you could just sit the thing down on your desk. It would join your network, and, you know, then you could go in there and configure everything without having to plug it in or do anything like that. So I was just curious. I don't do a lot with teensies. I've played with the smaller versions of them, but yeah, I do more with the ESPs and Arduino stuff. So
I've done it all with all of them. I've spent a lot of time working with microcontrollers. The big advantage to the Teensy is that it's able to do full duplex, full quality audio, and it has a whole lot of GPIO, and it is redonkulously powerful. So I knew I wasn't going to have to worry about whether I had enough CPU cycles to do all the things I wanted to do.
Yeah.
So that's why I chose the Teensy.
No, there's no question for your application. That's likely the best choice. I know the DSP capabilities of those chips are amazing. So
yeah, the Teensy 4.1 does have a 6-pin header for a wired Ethernet socket. You need to hook up an external PHY to it, but I haven't considered doing that on this at all. This case is not thick enough to be able to put an RJ45 socket on the board and still have it fit inside this case. Otherwise, I would have used RJ45s for some of these things that I'm using the 3.5 millimeter for. Like the cable that runs up to the boom, that would have been an RJ45 if I had the space for it, but I don't with this case. And
I'm not sure Ethernet capabilities adds anything anyway. You know, you plug it into USB, you plug it into Ethernet, you're still plugging it in, right?
Yeah.
So
cool.
Okay. Anybody else? All right. Well, I can tell you, I've belonged to the Groups IO page since you turned it on, and there's some interesting discussions on there. So if you're interested in this and you want to keep, and also Halibut Electronics is going to be doing some other projects. You want to real quick talk about the choke tester thingy?
Yeah. So I got 2 other projects that I'm working on right now at the same time. The first one, I don't know how many of you saw my presentation at the QSO Today Ham Expo from fall of 2021. But Paul has also asked me to present on that one to this club. And so we'll get to that at some point. In that presentation, I talked about how do you measure the effectiveness of a common mode current choke, also known as a 1-to-1 balun, using a nano VNA. So there are a bunch of ways of designing common mode current chokes with ferrites, and sometimes you just wrap them around PVC or wrap some coax around PVC, or ferrite toroids or ferrite beads. And there are all kinds of designs and wisdom and, you know, like rules of thumb on one side, and then like deeply scientific, like way over my head kind of math on the other side. And I never found anything that was nicely in the middle. There's a lot that tells you, okay, I've done all of this math, I'm going to boil it down for you just to build this. But I never found anything that was good at explaining why just build this was sufficient. And so what I wanted to do is I wanted to be able to measure the effectiveness of an actually built common mode current choke using a nano VNA. And to do that, you need to get the signal from the nano VNA off of the center pin of a coax and put it on the shield of the coax. Because what the common mode current choke is supposed to do is whatever signal is traveling on the outside of the shield, you want to choke that off. But anything that's traveling on the inside of the coax, you want that to pass through. And so, but if you're just running coax, like if you just put the normal coax of a common mode current choke into your nano VNA, it's just going to look like coax. The choke on the outside of it is completely transparent to any signal that's on the inside of the coax. So there needed to be a way to get the signal on the outside of the coax. And I built a test rig for that, which was literally just an SMA socket on one side, take the center pin from that and put it on the shield of an SMA, a BNC, an N, and an SO239 on the other side. And, now I've got like 4 different connectors in 2 different groups, one for the port 1 of the Nano VNA and one for port 2 of the Nano VNA. And you could plug in the coax cables of a common mode current choke, and it would route the signal to the shield, send it through the choke, and then route it, back to the center pin before it goes back to the Nano VNA. And then if you sweep that using your VNA, the log gain becomes a negative number, which turns into loss, and it tells you the dB loss of a signal being sent down the outside of your coax, right? And so the more effective your choke is, the larger the dB loss of that signal is going to be. So the Nano VNA worked out great as a way of measuring the effectiveness of your chokes, but you needed this test rig. And I had hacked mine together with some cables that I bought off of eBay into a plastic box. And I'm like, I don't recommend doing it this way. There's all kinds of stray capacitance and things like that. But because I was just doing one really quickly, I didn't think to try and build a kit for it. And then I had a lot of people asking me, where do I buy one of those? I'm like, you don't want to build it this way. And at the time, I'm like, I'm not getting into the business of selling kits. I don't want to do this. Well, guess what? I have since gotten into the business of selling things. Not necessarily kits, but once I realized that I was in that business and people were still asking me for these, I decided to design this board. On the backside is the SMAs. These SMAs go into port 1 and port 2 of your Nano VNA. And then there's a little switch here that changes the signal from going through the center conductor of these ports over to the shield of these ports. So it allows you to still calibrate it with the signal on the center conductor, and then you switch it over to the test mode and it puts it on the shield, and you can actually measure the effectiveness. But it's a simple circuit board with a bunch of sockets on it, with a bunch of connectors on it, and all the traces routed, impedance matched and shielded as best as it can be with a 2-layer board and whatnot. So this is a very simple thing. It's going to show up as a kit. You're going to have to solder these. But this was super simple. There's no firmware to support on it. So this is going to be my Hello World product for Halibut Electronics. This is the product that I'm going to sell first as a way of figuring out how to set up a shopping cart and figuring out how to take payments and how to submit sales tax with, various different organizations and whatnot, right? That's going to be a lot easier on a simple, roughly $50 or $60 kit than it will be on a more than 100, less than 1,000 complex radio. So that's why I went ahead and took the break to start designing this. I don't know if you can see these boxes right here behind me, but these 2 boxes right here literally contain all the parts to make the first 100 of these. I just got the top of those 2 boxes this morning, actually. So now I need to spend the time of stuffing 100 bags full of these parts and finish going through the process of setting up the shopping cart and being able to take payments and whatnot. And then this will be my first product.
Cool. All right. Anybody else? Well, thank you, Mark. This was fascinating. And I've been listening to this because I listen to the Ham Radio Workbench podcast, and this has been talked about in various forms. And when it finally became public and I saw the presentation on the QSO Today thing, and I'm eagerly waiting. I'm putting more stuff on eBay so that I have the toy fund to get one when they're ready. Because I've been wanting to play with satellites. I've got the Elk antenna. I've got the old school full duplex HT, but that, you're right, it takes like 8 hands to make all the parts work all at the same time.
Yeah.
So I like the fact that this one has the brains and does all the thinking for you.
Yeah. Well, not all of it. You still have to operate.
Well,
but at least it does
most of the heavy
it does a lot of the hands for you.
Yes. Exactly. So, all right. Cool. Well, thank you very much. You may now move on to the other things you've got going this evening.
No worries. All right.
And
thank you very much.
Yep, I just recommend everybody, if you're interested in this, following along, go to groups.io and look up the Halibut Electronics. Can you show that link one more time?
Did I close it down? Curses, I did. Go to groups.io and search for Halibut Electronics.
There you go.
Halibut is spelled Halibut.
Like the fish.
Like the fish. I'm also Smitty Halibut on Twitter. Paul can give you links to my Twitter accounts if you want, if you can't find it quickly.
Sounds good. All
Rock and
right.
roll.
Thank you, Mark.
Thanks everyone for having me.
Okay. Bye-bye.